Semiconductors. First of all, let's define semiconductor. A semiconductor is a material which has an electrical resistance in between those of insulators and conductors. So, definition of a semiconductor, yes, it is a material which has resistance in between insulators and conductors. As a matter of fact, there are two factors affecting the electrical conductivity of a semiconductor. So, electrical conductivity of a semiconductor depends on, first of all, the temperature, and conductivity of a semiconductor increases with the rise in temperature. Okay, and we'll explain this later on. Second factor affecting conductivity is addition of impurities, presence of certain impurities. When some certain impurities are added in controlled amounts to a semiconductor, the conductivity of the semiconductor increases. So we'll summarize all this in the following definition of a semiconductor. It is a metal that is characterized by the fact that its electrical resistance decreases with the rise in temperature and presence of certain impurities. Your attention, we've got something important here to mention. A semiconductor has some electrons in its lattice that are more tightly held than in a metal, but less tightly held than in a non-metal. Let me say it again. A semiconductor has some electrons in its lattice, crystal lattice of course. These electrons are more tightly held than in a metal, but less tightly, yes, held in a non-metal. We've got very important piece of information. At 0 Kelvin, okay, we call it absolute zero, a semiconductor is considered a perfect insulator. A semiconductor has no free electrons to act as charge carriers, okay? So it is a perfect insulator at this particular temperature, at 0 Kelvin. All bonds in the crystal are intact, they are unbroken. Okay, so once again, at 0 Kelvin, a semiconductor is considered a perfect insulator. And when the temperature is raised, number of bonds are broken. Then free electrons are generated, electrons are set free, and conductivity increases. At room temperature, as I said, a few electrons are freed, are set free by thermal excitation, and hence a slight conduction, just a slight conduction of electricity can occur. Raising the temperature of a semiconductor causes some valence electrons to become free, and thus the ability of a semiconductor to conduct electricity increases with the temperature. And now talking about pure or intrinsic semiconductors. Intrinsic semiconductors are pure elements such as silicon and germanium. So we use silicon and germanium. And let me tell you something, we prefer silicon, and you will be able to know why. So intrinsic semiconductors are pure elements such as silicon and germanium. They are tetravalent. What does it mean? They've got 4 electrons in the outermost energy level. They are tetravalent. Silicon and germanium are tetravalent. Okay, once again, at 0 Kelvin, all the valence electrons are firmly bound to the nucleus of their particular atom. At 0 Kelvin, all the valence electrons are firmly bound to the nucleus of their particular atom. So the crystal is considered as a perfect insulator at 0 Kelvin because of the absence of free electrons. At room temperature, the energy of a valence electrons may become greater than the binding energy of its nucleus. So it is set free, leaving behind something we call positive hole. It is shown in front of you on the screen. The covalent bond is then broken and an electron is freed. Okay. We've got some important hints here. First of all, the number of free electrons equals the number of positive holes in a pure semiconductor. In intrinsic semiconductor, small n is equal to P, okay, it is equal to Ni. Number of free electrons is equal to the number of positive charges. At any given temperature other than 0 Kelvin, a state of thermal equilibrium is reached. We reach a state, we call it a state of thermal equilibrium, where the number of bonds that break equals the number of bonds that recombine, so that a fixed number of free electrons and free positive holes, is there at that given temperature. As the temperature increases, we reach another state of thermal equilibrium. As the temperature increases, the number of free electrons and number of holes increases. That is to say, the number of bonds that break increases, and a new thermal equilibrium state is reached. And now talking about extrinsic semiconductors. Semiconductors, okay, which are doped with impurities, with certain amounts, okay? As a matter of fact, doping a semiconductor with a tiny amount of impurities causes a considerable increase in the number of charge carriers. Doping increases conductivity. Why? Because it increases either the number of electrons or by increasing the number of holes. So once again, doping increases conductivity by adding either electrons or holes. And now talking about n-type semiconductor. First of all, to obtain n-type of semiconductor, pentavalent impurities are added. Okay? Addition of a pentavalent element such as phosphorus, antimony, and arsenic. Any one of them will do. So addition of a pentavalent element such as phosphorus, antimony, or arsenic will increase the number of free electrons. So in n-type, actually we are increasing the number of free electrons. And I'll explain this right now. Antimony atoms have 5 electrons in their outermost energy level. When an atom of antimony is added to a silicon crystal, what happens? It is shown in front of you. It settles in the crystal lattice. The atom settles in a lattice site with 4 of its electrons shared with the neighboring silicon atoms. Okay, it has 5. 4 are shared, so we've got an excess electron. We call it free electrons. So addition of antimony will increase tremendously the number of free electrons. Okay? As I said, the 5th electron is not needed in bonding. And so it becomes free to move through the crystal. In the n-type semiconductor, the majority charge carriers are free electrons, minority are positive holes. Let me say it again. This is very important. In n-type semiconductor, majority charge carriers are free electrons, minority are positive holes. We've got something important here. Your attention, please. Adding dopant atoms, impurity atoms, does not add any net charge to the semiconductor. This is very important. So n-type semiconductor is still neutral. So let me say it again. Adding dopant atoms does not add any net charge to the semiconductor. The semiconductor is still neutral, as if there are free electrons, then there are the same number of positively charged holes and ions. That is to say, the crystal as a whole didn't lose or gain any electrons. So it is, yes, so it is neutral. It is still neutral. Okay, since impurity atoms give free electrons, they are called donors. So the dopant here, impurity atoms, are called donors because each atom donates, yes, an electron. They are called donors. At thermal equilibrium, the sum of positive charges equals the sum of negative charges. So n, small n, denotes number of, yes, thank you very much, number of free electrons. P, number of positive holes, and Nd positive is the number of, yes, donors, concentration of the donors. Okay, so once again, Nd positive is the positive impurity concentration. Small n is the free electron density. P is the hole density, or the number of positive holes. In this type, in n-type material, n is much greater than p. Number of free electrons is greater than number of positive holes. That is why it is called n-type material. And now talking about p-type material or p-type semiconductor. Okay, your attention to the impurity atoms that will be added in this case. They are trivalent. So p-type semiconductors are made by adding atoms which are trivalent to a pure silicon crystal. The impurity atoms may be boron, gallium, aluminium, or indium. Okay, so impurity atoms, each atom has 3 electrons in the outermost energy level. Okay, so 1 binding electron is missing. 3 are used in bonding and 1 is missing here. Okay, in this way an enormous increase occurs in the number of holes. So in the p-type semiconductor, the majority charge carriers are positive holes and minority charge carriers are free electrons. Minority charge carriers, yes, thank you very much, are thermally generated. The impurity atoms are called acceptors because each atom accepts an electron. And now your attention please, we'll make some calculations here at thermal equilibrium. Okay, P, number of positive holes, is equal to number of, yes, negative acceptors and number of electrons. That's why the crystal is still neutral. Once again, Na negative is the negative impurity concentration. In this particular type, number of positive holes is much greater than the number of free electrons. So it is called p-type material. And now we've got mass action law, and it is very important. Under thermal equilibrium, what happens? The product of the free negative and positive concentration is a constant. Product of small n and p is a constant, independent of the amount of donor and acceptor impurity doping. This relationship is called the mass action law and is given by the expression product of N and P is equal to Ni squared, where Ni is the intrinsic concentration. That is to say, Ni is the electron or positive hole concentration in a pure, yes, semiconductor. In case of the n-type semiconductor, since adding n-type impurities decreases the number of positive holes, so number of positive holes is diminishing. Small n, number of free electrons, is much greater than number of positive holes. The crystal is neutral because n is equal to, yes, p plus the concentration of positive donors. Okay, as I said, since p is diminishing, we can say n is almost equal to n positive d. P, number of positive holes, is very small, so it can be neglected. That is to say, in an n-type material, the free electron concentration is approximately equal to the density of donor atoms, mass action law, Np, which is equal to Ni squared. So we can calculate the number of P. It is Ni squared over N, and N is equal to the number of positive donors. So we can say P is equal to Ni squared over the number of positive donors. And what about the p-type semiconductor? It is still neutral because number of positive holes equals number of negative acceptors and number of free electrons. And adding p-type impurities decreases the number of free electrons. Number of positive hole is much greater than the number of free electrons. So number of free electrons is very small. Actually, it is diminishing. Okay. So we can say P is almost equal to number of negative acceptor. Mass action law, Np equals Ni squared, substituting. In this case, we can say small n is equal to Ni squared over P, which is equal to, yes, number of negative acceptors. So small n is equal to Ni squared over, yes, number of negative acceptors. And now talking about the PN junction. Okay. By a special manufacturing process, a junction is formed between P and N type semiconductors. Let me say it again. By a special manufacturing process, a junction is formed between P and N type semiconductors. Okay, it is shown in front of you. When the junction is formed, we expect free electrons to move, to transfer from the N type to the P type. And of course, positive holes will do the same from P type to N type. And we've got a layer called depletion layer, and a potential, we call it barrier potential. Okay? Your attention, this layer is very important, and as I said, positive and negative is produced, and this means we've got potential, we call it barrier potential. As a matter of fact, symbol of the PN junction is shown in front of you. Okay. And now we want to define the barrier potential of a PN junction. It is the potential difference. It is the potential difference between the N-type material and the P-type material, which is just strong enough to stop the flow of electrons from N-type to P-type semiconductor. As a matter of fact, the PN junction is operated in one of two modes. It could be forward biased or reverse biased. So the PN junction is operated in one of two modes, which are forward bias, reverse bias. We'll start with the forward bias. In forward bias, N-type crystal is connected to the negative electrode of the battery. P-type is connected to the positive one. Okay, what happens? depletion layer decreases, barrier potential decreases, and current flows. In this mode, the PN junction, yes, allows the current to flow. It acts as if it is a closed switch. Okay, talking about forward bias. So N is connected to the negative electrode. P is connected to the positive electrode. Negative electrode will push free electrons and make them, yes, pass through the barriers. So we say depletion decreases, barrier decreases, and current flows. And what about the opposite mode, reverse bias? A reverse bias, N is connected to the positive electrode. P is connected to the negative electrode of the cell. Okay, so we are increasing the difficulty here. Depletion layer increases, barrier increases, and almost no current flows. Okay. In this mode, the width of the depletion layer is increased, so the barrier potential increases, and almost no current flows through the diode. PN junction is called diode. The diode acts like a very large resistance. Almost, it acts like an insulator. And this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.